So what we have done throughout this little miniature nuclear chemistry unit is gone over the couple main ideas. One, that an element can change into a different element, which hopefully before this, that seemed odd. Because chemical reactions are trading places, not actually one thing turning into another. The reason why they do that is in order to achieve stability, because some isotopes are more unstable than other isotopes. Fusion and fission are the last topics we have with nuclear chemistry, because fusion can kind of occur on its own if we talk about the sun, so it doesn't have to be human done. Although fusion can be also done by humans, just like fission can. And these kick it up a notch. These take a lot more energy to make it happen at first, but they give off a whole bunch more afterwards. And I believe there's a more application to using this for energy sources in the future for our planet. Again, alpha decay is great if we want helium balloons, but not much else we're getting out of that. So that's why we'll refer to it more as artificial transmutation. Remember, transmutation is the element changing into a different element. Artificial means we are the ones that are making it happen. It's not naturally occurring on its own, just like the synthetic or artificial elements at the bottom of the periodic table. How fission occurs. And some people memorize the definition of fission being splitting an atom. Well, yeah. But it's not like we have a little laser that cuts an atom in half. What we typically do is we take an atom that's already unstable and we make it even worse. You think about maybe a person that you know or your own life, that if you've just had the worst day possible, and then all of a sudden one more thing happens. I mean, it might cause you to scream at the top of your lungs. It might cause you to cry. It might just cause you to break down and say, I give up, I'm done. If we take an atom that is so unstable and we add to it an alpha particle, a proton, a neutron, it is now in such rough shape that a simple alpha decay or a beta decay or a positron emission is not enough. It is so ridiculously unstable, it almost has to start from scratch. It's going to actually break into two pieces at that point. And that's what fission is. It's the splitting of a nucleus. But it's not splitting by cutting it with some sort of laser. It's splitting it by taking something that is so unstable and making it even worse. We're going to keep on piling on. Maybe not the best reference to give while I'm recording this, but a TV show that I like, which is very inappropriate, is It's Always Sunny in Philadelphia. And there's an episode where all the guys decide to break the sister of one of the people. So they put on this ruse of her becoming famous, and then they break it to her at the end because she was miserable before, but they wanted to show her, but no, there's a lower that you can go. And she just loses her mind at the end of this because she thinks that she's becoming a famous comedian, and no, it was all a hoax the entire time, and she just loses it at that point. Now you can see from the picture on the bottom, I have this particle speeding towards this nucleus. Because first off, it does have to go. I mean, both fission and fusion, there's going to have to be a fair amount of zipping that particle at something. And again, what happens is it breaks into two smaller nuclei. Now, typically, those things are not right away stable either. And that leads us into, when we talk about nuclear fission, that they deal with nuclear power plants. One of the problems with nuclear power plants is the waste product of fission. It is not perfectly safe. So when people are looking out for alternatives to burning fossil fuels for our power, fission is one of the things that are brought up. I believe almost half of France is powered by fission. I think it might be getting close to 20% of our country. But the nuclear waste is the issue that usually pops up when they talk about that. So these two separate atoms on the bottom are the issue. You can see there's 3 other small particles shooting off. We'll talk about what those do in a minute as well. Okay. If nuclear fission, the splitting of an atom, can give us energy, that energy that can power homes, power countries, we need to go over where that energy comes from. Now, the first point I have here is similar to that idea of gamma decay and radioactivity, that if you're unstable and you become more stable, you release energy because you no longer need as much energy to hold it all together. I believe this is where I gave you the example of me substitute teaching for a less than ideal class once upon a time. However, when we start talking about nuclear power, and in particular nuclear fusion, that I'll go over in a little bit. So fission, this is partially true, but I like the stable, unstable part. But when we go over fusion, the idea of what's called mass defect plays a role. And you can see in question number 2, probably the most famous equation in all of science. The problem is, most people have no idea what it means, other than, hey, that's that Einstein equation. But you're at the point this year where you should be aware of what that means. And secondly, not confuse this with other types of energy being released. And what I mean by that is this year specifically, we put the nuclear change unit at the very end of the year. We used to do this with the atom. Kind of makes sense. You know, you talk about isotopes, let's talk about how they're unstable then. But the problem we had year after year is that students then would think any type of chemical reaction that was exothermic is because it lost mass defect. Oh, that wasn't good. This only occurs on a nuclear scale. The E in that equation stands for energy. Kind of self-explanatory there. M stands for mass. After all, mass defect. C. You already know what C is. Does anyone remember what C is? Think back to first semester in the atom unit. We had a variable that was letter C. The speed of light. Speed of light is 3.0 times 10 to the 8th meters per second. I mean, that's really fast. I mean, if you ever hear people talk about that star out in the night sky, well, it's probably burned out a long time ago. It just took forever to get here. Simple thing as a track coach, we talk about if you're timing the 100-meter dash, you're at the finish line there at the start, you start to stopwatch when you see the smoke, not when you hear the sound, because light travels so much faster than sound does. 3.8 times 10 to the 8th is a huge number. E equals mc squared. If you take the tiny little bit of mass that's lost during some of these artificial nuclear transmutations, but multiplied by 9.0 times 10 to the 16th, so I squared this, a tiny little bit of energy can give, a tiny little bit of mass multiplied by a huge number can still give you a significant amount of energy. In particular, nuclear fusion shows this. The mass of the starting products and the mass of the ending products, there is a difference. A small difference, but there is a difference. And that's where that energy comes from. Fission, I think, is a little bit more of number 1. It's unstable, becoming more stable. But I have seen some texts that reference mass defect for any type of artificial energy creation. Last thing to mention is a chain reaction, and that's what my next picture is going to show you. In fission, when you have something splitting an atom into 2 smaller pieces, it's very common that there's a couple, let's say, neutrons that also are released. And since this is happening at such a high speed where that first neutron is splitting that atom, the things that are breaking off are now high-speed projectiles, we could think of as well. So now what does this guy do? It'll split this one up on the top. This one will split the one on the bottom. And when that occurs, it's kind of a domino effect. So the energy from one atom, previous slide explains between the stable, unstable, and the mass defect. But fission, especially fission reactions, they occur over and over and over again. So you have a whole bunch of uranium, for example, because uranium is one of our main fuel sources for nuclear fission. You have enough of this over and over again to get this domino effect where each of them is giving off a lot of energy. If you've ever noticed that a lot of nuclear power plants are near a big body of water because they need to cool things down to make sure they don't have a partial meltdown, which places like Chernobyl had. 3 Mile Island in the United States was close to having. I forget what the city was in Japan most recently because of, was it a tsunami that then threw everything off? So they had to be by the water in order to cool things to keep it safe, but then that was the downfall for them at that point. So we get this energy by splitting an atom. And I just want us to be aware of splitting an atom doesn't mean taking something unstable and we're making it ridiculously unstable where it just has to break apart. And that breaking apart makes more stable things, and typically there's a little bit of loss of mass defect. Now fusion is the exact opposite of fission. It kind of lends itself to vocabulary for students at times. Fusion is combining two things to make something bigger. When I talked about the elements at the bottom of the periodic table that were man-made, that's fusion. Next class, when we wrap up this entire year of content with where the elements came from, it's going to be fusion. Again, the key here, just like with fission, is something more stable occurs. But I know for every explanation for fusion I've seen, mass defect is related to the energy. And actually, fusion gives off even more energy than fission does. Now, unfortunately, on our planet right now, we don't have nuclear power plants that are based off of fusion. They're based off of fission. So the best example I can give you is the stars. The video I show you in a little bit is going to kind of demonstrate that some more. If somehow we could get fusion to be like in nuclear power plants, the advantage of fusion is it doesn't give off radioactive waste typically, especially if it's just hydrogen fusion, which is the most common type to do. Our planet has a whole bunch of water on it, so water is H2O. We got plenty of hydrogens available as well. Have you ever heard the term cold fusion? Cold fusion is referring to the fact that in order to get this to occur, to get two atoms to combine, I mean, think about it, there's protons. Protons repel each other. We want to get them to smush together to make a new element. They have to be going ridiculously fast. We have to put a lot of energy into colliding these things to make them stick together. Currently, it takes us more energy to get fusion to occur than we get back, which is not a great power source then. If you're putting more in than getting out, I mean, that's what makes burning fossil fuels so easy, is you get a lot of output and not a lot of input to make it happen. I mean, there's drawbacks with pollution, but the positive of burning fossil fuels is it's easy. You get more than you put in. The problem is with fusion right now, we haven't figured out how to make that happen. Because again, if we talk about stars as the main place to occur that with, inside a star, there's a lot of gravity pushing in. And when that happens, it's smushing things together just by gravity, a natural force. So it's able to make things get together without doing a particle accelerator. Up on the board, besides the picture of the star, very common hydrogen fusion would be between two unstable isotopes of hydrogen. Hydrogen with a mass of 2 and hydrogen with a mass of 3. deuterium and tritium. And when they fuse together, if you look at my nuclear equation, they create helium. They make the next bigger element. And then the neutron is released as well, and a lot of energy is given off. So what we want you to be aware of when it comes to fission and fusion is, first off, the difference between the two. Fission is splitting an atom, big unstable thing breaking down into smaller. Fusion is making one thing. So making a bigger thing now, as a matter of fact. Where do they occur? Again, fission, we can talk about nuclear power plants. We can talk about the bombs that we dropped during World War II. If you ever heard of a hydrogen bomb, that is a fusion bomb. We actually have dropped those in test locations. You can look up Marshall Islands at some point and see what the United States did to that area on a test. But otherwise, stars is the best example of fusion that we have out there. So my last